Okay, the recording is started, and now let's also start the screen sharing. Mm, okay, that was the wrong button. Okay, you should see the virtual machine now. So let's continue where we left off last week. So as you remember, last week we taking a look in how Qt on a very superficial level works, and we created a very humble beginning of a text editor app. So we have a text field and 3 buttons to load and save the content. So now let's give it something to actually do. So here text edit clear. Obviously making a new document is extra easy. We just clear the content of the text edit. Opening is a bit more fun. So here we want to show a dialog which will ask the user to provide a file, and this is in Qt quite simple. We need the QFile dialog class, and it provides a static function get open file name and a get save file name, which takes a pointer to a widget and then a caption to be shown. So we can say test open file, and you see this tr macro here used. It is a Qt mechanism to enable translation of the UI. There is a Qt tool which will go through the whole source code and extract all the strings where this tr is used, and the tr as such will invoke a function that allows to replace all of these texts with texts that can be provided in translation files. So this way you don't need to make your primary application binary aware of multiple languages. It is enough to write your application, let's say, in English, and then you can later on add a translation very easily. There is one limitation that needs to be taken into account. That is that for this mechanism to work, you need to properly initialize it and then add something that will allow you to load those translations. So there is at least something you need to take care of, but it's quite a little amount of code. So just that you know, for now we won't do that. It's just good to know that if you are writing a Qt application, you should just always wrap all the strings in this tr, even if you don't intend yet to translate them. Doing it instantly doesn't really cost you any time, and it allows you to later, with a few lines of code, add full translation support. The way this function works is that it always returns a string, and if the user pressed cancel, then it will return an empty string, in which case we want to break out. And if the user selected a file, then we have a proper file name. Qt offers a lot of classes which are very convenient to use. That allows us to do many things that normally, if you would want to do it with native functions on the various operating system, would require a bit more code. So for example, it provides a QFile object which represents a file, and it just wants to be given a file name, and then you can start modifying or reading and writing to the file. The Q file as such is derived from a Q file device, which again is derived from QIO device, which is then just derived from Q object. The QIO device is a base class which provides most of the functions that you would expect to find on a file, but also on other things. It is a base class for sockets, for example, for pipes, etc. It can also be used as basically a base class for anything that allows you to read and write data from. So it is quite versatile. Okay, and now of course we need to open the file. So file.open, and we need to specify how we want it to be opened. So file, in this case we only want read only, but when we see under definitions we could select write only, read write, append, truncate. Truncate is in flag. And also we could specify that it is a text file, but usually this doesn't really bring any benefits, so we won't do that. You could also specify that you only want to open files if they already exist. In normally, when just using normal open, this won't be necessary, but when opening for write, and open for writes always succeeds in Qt on a non-existing file just by creating a new file. But if you would want, in that case, to only open a file and write to it if it exists, then you could use that flag. And of course we can have a check whether that was successful, and if it wasn't, for example, we didn't have the permission to open that file, then we can just bail out. We could show an error message actually, so maybe let's do that. Q message box. Let's go with critical. That's the white X on a red square. Title. So just a window title and the message. And this tr has a mechanism that allows you to use this % something placeholder, so %1, %2, %3, and so on. And they can then be replaced. So you write arg like argument, and you can put an int, a string, whatever you want. Many types are supported into it, and this basically returns you a Q string, and on this you can make another arg, and another, and another, and it will always replace the argument with the lowest number that it finds once the arg is invoked, and then the next arg takes the next argument, and so on and so on. It's not super efficient, but for UI applications you usually don't need efficiency. I mean, here we just create a string to report an error, and then we are done. And as you see, there are quite a few more things that can be specified for a message box, but just to show it without anything else, this is enough. Okay, so at this point we have the file open, so we want to read the file's content. And many very basic file access mechanisms usually just offers you some sort of read comparable to these two functions. Either you specify a length. Basically, the normal Windows API just gives you this. You specify a buffer to read into, and the maximal length, so the size of the buffer, and the return value will be how many bytes were really read. Qt has like a simplified version which returns a qbyte array, which is an object that holds, as the name suggests, an array of bytes, so it holds a buffer. So here you just specify the max length that you want to read. But if we want to read the whole file, there is a read all as well, which allows you to read the entire file in one go, no matter how big it is. Of course, if you do that on a multi-gigabyte file, that will fill up your memory rather quickly. But it is doable, and for many smaller files it is quite convenient. So we go with qbyte array. let's call it data. Okay, and now one more thing, we need to set this data to our text edit. So UI text edit set plain text. And there is one thing to consider. This data are just the raw bytes. If we have just normal ASCII text, this is good enough. But if you want to use special characters, Chinese characters, like if you want to use very special characters, normal ASCII of course has like a basic subset of special characters, but if you want to use a smiley character or some arrow, or as mentioned foreign language characters like Chinese, Japanese, etc., you need Unicode. And the typical way how these data are encoded is UTF-8 because it provides the ability to be very space efficient and at the same time covers the whole Unicode range. I see there is a question in the chat. Yes, so the Q message. So the question in the chat is what this Q message box is, and yes, it is just a message box that will be shown, and the user can press OK. Okay, let's continue back. So usually if we have complex text files, we would expect them to be UTF-8 formatted. So here what we want is a Q string from UTF-8. And then we just feed it a byte array. If we would just do it like this, this would be equivalent to so let's fix that. Q string, that must be Q string. So not doing anything is equivalent to this from Latin 1 because that's like the default ASCII character set. Technically ASCII is just 0 till 127. Latin 1 is extended by the other half of the byte with the typical characters that you can find in Europe like umlauts, L, and other things like that. But as mentioned, we want UTF-8, and this is not done by default because as you have seen, there are quite many other conversions. So there's only one default conversion, and it's the simplest one. And the last thing, of course, to do is for good measure we can close the file, which is good to do, but in practice when the QFile object goes out of scope, Qt will close the file anyways. So close file is really needed if you have the thing in a loop or something and the file is outside of it. So let's quickly test if this really works. Open file, and voila, it works. So the next thing will be, of course, to write to a file, and this we will leave as a homework for you. Run. Okay, and it's quite simple. You can use the same function, just need to use get save file name. With open instead use write only, and then of course instead of reading file you're writing to it. So that should be a very simple homework and not too complicated, so a good start. Good. And now since we have this, let's see if we are missing anything useful from the last from the other project. Let's open it. It was Qt core test. Let's see. So main, yeah. So we had the thread we showed the communication and how these events can be invoked. Okay, so we could implement a bit more sophisticated test case. Here, because what we didn't do yet is I think we have not sent an event properly from one thread to another, so we will create a second thread. Here we only sent an event from the main thread. So let's comment everything out. Okay, and let's create a few more classes. And it's thread 1. And thread 2. Then we will create a few classes which will live inside of our threads. Class 1 through 4 or something, all derived from QObject. Fortunately you cannot create multiple at once. We could of course just copy and paste the file, but then you need to change all the names, so it's not really any faster than just using the wizard a few more times. We can start maybe with let's go with 4. 2 classes for each thread. C class 3 and C class 4. As you may hear, my voice is still not quite recovered, but it's much better than last week, so I think we might manage to do a bit more today. Okay, so let's set up first our threads. They don't need much. We need a QObject and a constructor. A destructor. We could add a destructor actually, that would be nice. Such that and for the destructor we'll add a wait. So if we invoke it from the main thread, then what will happen is that instead of corrupting everything, we will just gracefully wait until the thread's terminated. And I'm thinking what else to do here. We will not add yet any run or so, since the default run should be good enough for our purposes. So let's again go to main. Of course we need to include more things. Thread 1 and 2. Then we create them. That already invokes the constructors. We could in principle do everything before we invoke the event loop of the main thread, since we are not really using the main thread's event loop. But for now let's do it this way. Also the destructor of those will be called automatically once we go here out of scope. So we could maybe change this to be more explicit and create a thread on the on the heap, and then we can thread 2 must be here. Delete thread 1, delete thread 2, and there is a nice Qt function called delete later, which might also be useful. So if you are stuck in a slot somewhere and you want to delete some object that you encounter there, but you don't know whether there might be other invocations of signals on that object, you can use this delete later, which will ensure that Qt deletes the object for you once the last event that is scheduled for it has been deleted. I see there is another question in the thread. Is there a reason why we create a class per thread? Could we just throw functions into the thread pool and join them as we need them? So the reason we create a couple of threads is so that we can add a different thread logic to them. So currently we haven't done this, but we have the ability, as we did last time, to define this run function and then make each of those threads do something else. Which makes setting up things easier. So I can demonstrate this by here quite nicely. So in this case we don't have any run, so if we create new objects you would need to do it like this. So let's first include that the other objects, class 1 through 4, which are not yet Q objects, so we need quickly to fix that. No, they are Q objects, we're just missing the Q object macro, and we are missing a constructor. Let's quickly do it. And the desktop to a forward measure. Of course, need to replicate it. We will later also, of course, need to fill in the implementations in the CPP files. So before this compiles, there are a few more steps. Oops. That need to be taken. So we have this. Let's go back to main. So by the way, we can pin elements, and we can also. Where's the option for that? Should be an option to. Yeah, this one is nice. Then the pinned ones have their own row. Okay, so now we would say class 1. Okay, the class doesn't get an owner, and then we can move to thread 1, as we did last time, and so on and so on. And what we can do alternatively to this is we can just go to thread 1, create our own run function, thread 1, then we of course need to include class 1. And if we create, this is only needed in data, and if we create our thread here, it is created already inside the right object. We don't need to invoke move to thread. Also, we can attach this as a property to our object. And once we are done using it, we can just delete it. And it's safe to call the normal delete after exec terminated, because then we know that no more things can be queued to be done with any of those objects. And also using delete later after exec terminated will result in the object not being deleted. Okay, so let's see what else is missing. We will need to start, of course, those threads. Thread 1 and thread 2 must be started. The constructor is pretty much trivial, it doesn't do anything. Just calls the parent constructor and passes the parent argument, which we are not using. The destructor, we will make it a little bit more sophisticated, because here we will wait just waits until the thing terminates, and we could also add a quit, just in case, or if is running, then quit and wait, else nothing. This approach, of course, assumes that we are doing this exec. If we would use if we would run some code which is under our control, then we would need to implement some own mechanism to initiate the quit. There's another question. We don't need the return value of the main thread, but the main thread should return something, so we can just here also just exec and then return 0. That's fine enough. Okay, let's continue. So in thread 1 we already have the implementation done. Let's see for thread 2. Okay, thread 2 is done as well. Yeah, and we also need all the classes. So from just the first class we will copy prepare that should be another point, object parent. And actually we don't need the destructor unless we just want to log a log line or something from it, which we might want to do later, but for now we just leave it as is. Okay, class 1, class 2. Class 3 and class 4. Okay, should be all we need to make it run. What we of course are still missing are connections and additional objects, so let's go to our thread here and create the other class as well, class 2. And we are of course still missing signals and slots on the other thread, and on all of these 3 and 4 classes. Thread 1, so class 1 we actually need to include class 2. And then let's go to the other thread. Just copy this. and 3, 4. And so that we can connect those classes to each other, we should also implement some mechanism. So, for example, we can keep them protected, not public, and add a friend class. So thread 2, so the two threads can access each other's objects. Okay. Good. So let's do one more change. We will only start one thread and not the other. And the second thread are connected. And set sign. Can we do it some more elegant way? Because the thread is not yet initialized, so the objects don't exist. No, that is not the most elegant way to do it. Let's let them remain running, and to connect them it's the thing that makes it complicated. So this approach would be simpler because we would have the objects, we could connect them, and then we would start the threads. But here, the way we did it, the objects start existence once the threads started running. So what we will need to do is we will need to decide which of the threads should have the responsibility of connecting, and then synchronize on the other thread having already started. So to do that we will need to complicate the things a bit more than I wanted for the first demonstration. Yeah, let's not complicate things too much. So we will change this such that we will initialize those externally. So that it is simpler, and then we of course need a different access approach. We just make this public, or we could have a or we could also do something other. We could have a set function, right? Set objects or set classes. And then we just implement that classes 1 and 2. This one, leave this as private. Classes 3 and 4. Okay. Could of course use the constructor for that and add a few parameters to it, but let's keep it this way. Now of course we have to thread this class 1, class 2, we copy this for the other thread. Okay. Good. And last thing we want to do is we want to create objects on signals and slots on the classes, and we will want to connect them as well. So in principle not complicated as well. I think connect will not be happy if we call it after it was moved to the other thread, but we can try that if this complains or not. It should not complain, so that won't be that difficult. So we create class 1 through 4. And thread 1, set objects, set class, call it set classes, class 2, and the other thread gets 3 and 4. Okay, we have it already moved to the other thread. So now we should be able to let's say pack 1 signal signal 1 comma pack in another thread 3 one. Right, and connect we need again to specify the namespace. Okay, so we now of course need a signal 1 on class 1. And a slot 1 on our class 3. And this one needs a body, remember from the last lecture. And again we'll print there's another question. So the classes we are creating, class 1 through 4, are needed such that we have objects which will live inside the threads, as we demonstrated last time. To have the signal, the slots triggered in the other threads, then the objects the slots belong to must be in the separate threads. And the idea here is just now to demonstrate that we can have like 2 independent threads doing something, communicating with each other through these objects, and the main thread just waiting for everything to finish. Okay. And now of course need to somehow invoke this. So we can go to our thread 1, and before we even execute we can just emit class 1 my signal 1. So when the first thread starts, it will call inside thread 2 this function. And as you see, it printed correctly. So our connection works. We could connect those signals even if and slots even when the objects have the threads while they have already been assigned to the objects. And now to give some of the threads something else to do, we could, for example, both of them give a timer that will after some time terminate them. So q timer. I guess this needs to be included. Timer has this single shot function where you can provide a target like this and a slot like quit, and the time sorry, the time is first when it should terminate. So let's say after 1000 milliseconds. So this we will do for both threads. So both threads will after 1 second quit. And in the main thread we actually won't start the event loop, we'll just use the distractors to wait on the termination events. That sounds a bit faster. Let's make it longer, like no 5 seconds. Something's not quite right. It should wait for the thread to terminate, but it quits instantly. Let's see if this is working properly. So we'll put a breakpoints here, so we see this is running. Then we do quit. Yeah, right, well, we do quit, obviously, that's the thing. We, in this case, if we want to do it this way, we don't want quit, but instead we just want to wait until the quit that we have scheduled will be invoked. We will need a main event loop, because then because the main thing lives in the main event loop, but then we won't but then we will not get out of that event loop. Can we make this somehow more elegant? Yeah, we can. We leave the quit there. Move this from here. We'll just put our timer into the main thread and kill the main event loop instead. This will be we need to include QTimer again. And now here, since we don't have an object, actually we can use reference A. Okay, so this should quit after 5 seconds, and as soon as it quits, it will terminate the other threads as well. Yeah, and everything is closed. Okay, so let's see what we could now do here. So one thing, of course, what we can do is we can add some function that will take some time to do something. So let's say let's get here a not here. Not here. Private slots. Void my task. So this will take some time to complete. It can be called as a slot, and Let's implement it. So include QDebug. Let's make a loop for and here we need to include this as well. In say 1 second. Okay. So this belongs to thread 1. So let's go to thread 2. And in thread 2 we will want to have a slot that does something. So we'll need on our class 3 a signal. We'll do it differently. But for that we will need to at some point communicate the object between the two threads. So first of all, let's see, thread 2 yeah, we will not do that. So we have our task, so we can use the timer again to invoke it. Single shot. Let's say sometime after the thread was executed. No, one more thing to change. This we want now on this thread, so let's move this to the class here. So timer and then class try. Not tasks not. So this will be started after some short delay inside the current thread. We go to our tasks node. Okay, it doesn't find it. In class 3. Now we will need to find a way to get the other object. So we go again to our threads, and we will update here the implementation such that we always set all 4 objects on all 4 threads. Need to keep in mind that some of the threads belong to the other and we are missing the definitions too. That should be fine. Why is it complaining? Thread 2. Fine. Ah. Okay. Class here. Okay, and of course in main okay. Okay, so we have this. So now we can go to our thread. Let's see. So we have implemented the task on class 3. So we want to trigger it from thread 1. So we have, what did we? Tasks not okay, and on 1 we have our my task. Okay, so here in task slot we can first connect. Or we can use the invoke function, that would work as well. If you want to wait, so we used the invoke function already here once. It allows us to call a something on a different thread without the need to connect it first. But then we will need in our class 3 a reference to our class 1 such that we can address it. So maybe let's do it with a slot, that will be more elegant. So class 1 has this task slot, and we'll need a task signal. Let's say it will get an integer argument. So from no one is the one that executed, so this should be done in the free. So it will have a task signal. We can add as a return value. It's the two arguments, arg1, arg2, and a return value. We need the same arguments on our class 1 signal 1. And that was the wrong one here. And once you're done with this, that's too long, let's just go with, or let's just leave it as this and just make it faster. Then that one is like, we just want something to do here. Sorry, not thread, but arc1 and arc2. Okay. Now we go to thread 1 and then we want this to be here. So we have one signal, we have this task on class 1. Class 1. Oh wait. It's not great to choose the names, so similar. um, Here we need we have this, we have emit0, this is, so then we go to task 2. We have here on task which invokes this is fine. Then we need to also do the connection. The sender will be class I. Signal will be, it is task signal. And target receiver will be class 1, which lives in the other thread. Let's copy this and then just grab the slot name. My task, okay. And let's everywhere add any information from which thread they are. So here let's add quite a couple log lines. Okay, let's start with here. Is this what we want? This is static, that gives us the current thread. We want the thread ID of the let's see whether that works as expected. Yeah, that should actually work as expected. Okay, static thread 1, thread 2. Starting thread 2, then we have this task slot, so here we already have some, but we'll add an info from which slot this is. Like this type, let's cast it to a I think now it will complain each time everywhere, so we need to correct this. Let's go with the Qt version. I'm missing here an include hash. Did we forget something? task signal class free public slots. I think we wanted that to be a signal. No, task slot. So our tasks not meets a task signal. Signal is where it should be. Ah, that's I see. One more thing, I think that we need to change the connect, and we need to change to blocking because currently it's not blocking. You can see that when we go to our class 3 here and try to print the return value, it will print it will print 0 because it won't be waiting for it. You see here it printed 0, so what we need to do is we need to go to thread 2 and change this the connection type Qt blocked Qt connection. Yeah, so now the way this works is that one thread starts, so thread 2 starts a timer which will start this my task, which will enter here. It will be executed in the thread number 2. So wait, it starts this. It starts this, which will be executed in thread number 2, which then emits here a signal, task signal, which will be executed in thread number 1. The F12 is not always reliable. It sometimes jumps to the header and sometimes it jumps to the implementation. So it will jump in here. This will just do something so that it waits, and then it will actually do the operation we want. And once this is done in class 3, this emit will resume, and then the return value will already have a valid result. And you can, I mean, it's difficult to make a simple test case because it always becomes too simple usually. But this should more or less show you how you could connect more or less any amount of threads with each other such that they can call functions on each other, and this being done in a blocking way, so such that you nicely can wait for the result inside the function. Is this clear so far? Any questions? Okay. If there are no questions, then let's take a look on how if we wouldn't have Qt, we could do some sort of simple enough multi-threading. So let's create a new project. But I will for starters create still a console, a Qt console application, such that we can, if we want, use some Qt things inside. So this will give us some additional flexibility. Is that a good idea? No, let's run it separately. Let's just create a normal console application, and then we'll create a separate project which will then use some of the Qt mechanisms. So this thing is to include Windows H. Since if we don't use Qt, I cannot do things in a platform independent way. So here we will use it using the typical Windows functions. So on Windows, if you want to start a thread, you use the create thread function. It takes a few arguments. First is a security descriptor, which we don't care about, so we just null it. Stack size we can specify 0, then to just take the default. And then we need to specify an address of a function that will be the entry point for our new thread. So as you see, it's much more simpler, much more straightforward. Like in Qt, you need to create an object and so on. Here in C, you just need to have a entry point function. Of the right type, and we will give it a name, my thread entry. Okay. The next thing is a parameter, which is this value. So like in Qt, since you had a whole object, you could easily add different variables, strings, integers, complex other objects, whatever you want, in any quantity, and then the thread internally would use them. Here, since we don't have any object, we could either just pass one value, or what is usually done in such situations is that one creates some helper structure. My parameters, for example. And there we can add members, whatever I want, and as many we want. So we have our param structure, and since the thread might live longer than the thread which created it, this param structure should not be created on the stack, but it should instead be created on the heap. New is params. Farm1. Let's make some. Then we can pass this. We just need to cast it. Although here it should auto cast, since the LP void is any pointer can be casted to LP void, so we don't need special casting. And the last two things is a flag, which will allow us to set a few thread properties. One of them is the create suspended, which allows us quite nicely to suspend the thread in its execution. So when it is created, it will not instantly start executing at its entry point, but instead it will wait until it is resumed. And the last one is a reference where we will receive the ID of the newly created thread. This is not usually needed, since we are also getting a handle to the created thread as a return parameter. So since we created the thread, now we need to, in the suspended state, now we need to resume it. And as soon as we call this resume thread, this is non-blocking, so we continue further down, while here this entry point at some point will be executed. So one thing we want to do, for example, might be to cast our input parameter to our params. Let's add here a 0 and the breakpoint. And another thing we might want is to wait until this is finished. So we can use wait for single object. And we can specify how long we want to wait. If we want to wait forever, we just specify -1, or there is the infinite template, which is effectively just -1, as you see. And of course returns 0. So the sequence should be that we run until this breakpoint, then we enter this breakpoint, and then we enter this final breakpoint here. Zack. So, as you see, doing it on a low level without all the Qt stuff is, in a way, simpler, but at the same time, of course, you need to at least create some object if you want to pass some arguments around. So, it is not completely trivial, let's say. It, to some extent, has at least some level of convolution. So, also you need to cast on the right type, so there are more opportunities to undo a mistake or something like that. Good. And of course this way you can create as many threads as you want. In our other Qt example, here we could of course also create multiple, where is it, multiple instances. So we could create was it thread 2? Yeah, thread 2 is the one that starts at that. So we could create a couple more thread 2s, 2 A, B, and C, and I know that will not work because we need to still assign the objects further down. So here we would need of course to assign, and it would be it is not that simple because objects 3 and 4 we would need to create copies of them. So for now let's just not do that. But generally speaking, you can create many threads and reuse them as well in Qt. That's not a problem. Okay, so now let's take a look on thread synchronization. So since we can create one thread, we can of course create many threads. So let's do that. Let's include a few useful things. Well, that should actually be maybe map. Okay, so let's say we want to create 10 threads. So we'll create threads, and then we need to have a vector of threads. Vector handle threads. We'll collect all the threads, and one more thing, of course, we need to close the handle at some point. So at the very end, let's do it differently for threads, because we have many threads. We should have range loops in this. Which version is that? Should be new enough for ranged. For range loops, but I can also just do it by hand. I've already here before. ESLS 10. so that we close all of them. And here what we can do is we can either wait for each of them, so we could put this here. For now, let's do it this way. We just wait until all of them are finished, and no matter in which order, and they all get started here. So we will have quite a few of them. So let's pass to all of them. All of them will get the same argument. For example, here we can add a std list of integers. And we'll just and here with this we will create a new param for each of them. And of course, before we terminate, we need to dispose of it. So you see there are many individual steps you need to think. You need to remember that you need to delete params, you need to remember that you need to close the handle, etc. with Qt. All of this is done automatically for you, but on the downside it makes other things more complicated. This we want to be a pointer, pair list, and we will create here list std list list. My list. So this list will be shared by all the threads, and as soon as we start using it, we will run into issues. So every thread will just put into the list its own number, and there will be 10 threads doing this concurrently. So obviously once we are done, we expect there to be alright, it only does it once. It is of course not often enough to be interesting, so let's go with 4. Let's go with 1,000,000. So the threads will run for a bit and pushing their own number onto the list. And since we don't synchronize this list, we expect that either the application will crash outright during one of the push operations, or it might arrive at the end, but then still we will not have the right amount of elements in the list. So let's run it. Okay, it's running. Okay, and it's done, and let's see how many elements we get. Well, this is not quite 10 million, so something went wrong. And if we actually continue execution, when deallocating the list, it actually crashes. So what we learn here is that usually you cannot access an object from multiple threads just without any synchronization. So ideally what you want is you want to first obtain exclusive access on the object, so that you know that no one but you can access it, and then once you are done with whatever you are doing, then you can release the access, and then the next thread will be able to access the object. And Windows provides a synchronization mechanism which we could use here. It is called a critical section. Initialize critical section events, and again you need to manually initialize and destroy it. So how was that? So using more modern objects which do those things for you is of course more convenient, but also adds some overhead. we can here enter critical section, palms, and leave. And now this ensures that so at any point in time only one thread can be inside here this code block. So enter critical section will block until there is nothing that is having a lock on whatever resource we are guarding. Then we enter, the resource gets locked, so any other thread which might try to enter will need to wait. And only once we say here leave critical section, one of the other waiting threads, there can be many, will be resumed. So let's run it. Okay, and let's see how many entries we have at this time. Okay, something didn't something wasn't right because well, we didn't corrupt the whole thing, but for some reason we did not get the 10 million entries we actually expect. But at least we don't crash. This is already an advantage. Let's see why we don't create enough elements. One of the threads must terminate prematurely. We can just for testing run only one thread. Oh, sorry. I have hex display enabled. That shows us, of course, hexadecimal. I didn't notice that. Everything's fine. Once it's done, we have the expected size of 10 million entries. So as you see with this synchronization, it already works. And if you want to do more or less the same, but in a more modern way, we can please do that as well. So what we can do if we have a modern version of C++, we can actually use the STL library to implement synchronization. What do we need? We will need thread, and we will need mutex, and we'll need mutex enough, thread and mutex enough. Okay, so we have main, and using the STL you can also create threads using the thread object. Let's call it mythread1. Let's do that also in a loop. So let's start again with a std vector of threads. This will not be that easy. I think this thing is a template, so it might be more difficult. It will be difficult. So here it was quite easy to put it in a list because all the types are always the same, but here when we have our thread, since it's a template, let's see what it's not a template, it only takes templates for the constructor, then it might work. Let's try it. Threads. Let's make this pointer. So for mythread asterisk new thread, and this takes as argument either a entry point, like this thing, or what it also takes is a lambda function. Lambda function is like a function which you just write directly where you are, and the nice thing is that then the code is usually more readable. Okay, pushback thread. And now once we created all the threads we want to wait for the threads to finish. So just call threads at e point on all the thread join, which is more or less equivalent to waiting, and we need to delete them. Now what we could do, since we have STL, we could use here a smart pointer. Smart pointer. Okay, so this needs a few changes. Okay. And this way we don't need to delete it, because once the array, the vector here, goes out of scope, the smart pointer, the shared pointer, will automatically call delete on all the elements that it contains. Okay, let's now see how we can do the other thing. So here we have our list again, and what we can do is well, there are two things we can do. We can either pass the list here, the simplest way, in the capture list. So this way the list will be by reference passed to the thread. So this lambda functions are quite nice, because you can, as you see here, just capture elements from your scope, and then you can access them here. The other way you can do it is you can just pass arguments. So in this case we would go with asterisk playlist, and then here you can just pass an argument reference my list. Okay, and here inside we can then my list, that was playlist, pushback, and let's here capture the I value by value. Then we can use pushback I. And the I here, since it's captured by value, when we have multiple threads, each thread will have its own copy of I, so it will push back the right number to the list. Of course, still here we are missing synchronization, so running that would cause trouble. So what we then do is use std mutex. This will need to pass here as well. Let's do it as argument. Let's call this my mutex. Okay, so we have our mutex, and similarly we can just lock it and then just unlock it. So at this point, this will just do the same. If we run it, we'll just get at the end 10,000. Sorry, not 10,000, 10 million entries. We can just run it. We don't need that breakpoint. We forgot the loop that makes it 10 million. So this way we just got 10 entries. Now it's 10 million. Let's run it again. Let's try it can take some time. We can then, as next step, compare the execution speed of those two. As you see, it's still properly synchronized. And since STL is so useful, it gives us yet another very nice tool. Unique log. Do we need to include that? Okay. So this object, this log, will be created on the stack once, well, at this moment, and once it goes out of scope. So and once it's created, it will execute mutex log, and when it goes out of scope, it will do mutex unlock automatically. So if we, for example, would have the old code, like this with the unlock, well, it should still work, but if we, and let's reduce this so that it's really quick. As you see, it 10 minutes. If we would forget the unlock somewhere, then the result would be actually it throw us an error, which is also nice. Yeah, because it was already logged for the same loop. But if we, how can we make this fail? We can just make a lock and then return or break. So the thing is smart enough that when it's inside the same thread and it's locked twice, it will assert. But now, since we exited, when we take a look on the process, we will see that it's not doing anything. It's just sitting there and waiting with all its threads forever. And the reason here is that what happened effectively now is that all the other threads are waiting for their mutex log to actually lock. And this is a thing that it's easy to wrong, that if you have somewhere multiple mutexes and you are locking many objects, that you lock things either in an order that will make it unable to the final lock, or that you just forget to unlock somewhere. So if you would have actually the unlock, but then some condition and break before the unlock happens, then we would also end up in a deadlock scenario. Using this locker mechanics alleviates this issue, because this thing, you cannot forget to unlock it. When it goes out of scope, it unlocks automatically. And of course, Qt has also a QMutex and a QMutex locker, so the mechanisms that are available in the Sun template library, many of them were available in Qt long before they were part of the standard template library. So that's that. Are there any questions so far? Okay, if there are no questions, then we can take a look on how such synchronization mechanisms like this locker actually work. So internally, of course, the implementation is rather complicated of both the critical section and the std mutex. Generally, the way it is made is such that they are using some CPU instructions which have a atomic nature, so that they get executed even if they're complex, either entirely on, not at all. And this way they first test whether the object has currently some sort of contention, so if there are multiple threads which want to access it. So usually this is just a pass-fail test, so that either they get a lock instantly with next to no CPU usage, or they fail. But if they fail, then they see okay that some other object has a lock, so somehow this contention needs to be resolved, and in this moment the function is delegated to the operating system. So the Windows operating system has a couple of synchronization objects which behave pretty much similarly to this mutex. They are also called a mutex, but the difference is that to use them you need to call the operating system to do something for you, and this takes always much longer than just executing a couple CPU instructions. So all the modern implementations of mutexes first use some fast method to detect if there is a competition for a given resource, and only if they don't obtain a lock instantly, then they will invoke the operating system. So one thing we could of course do is first we could just directly use the operating system mechanism. Well, let's leave this here, and maybe let's go back to the above code base. Okay, so we return to our top code base here, which is more basic, and instead of the critical section I will try to use a mutex directly. So first of all, similarly to the critical section, we need to create a mutex. As all the Windows objects, mutex is also just a handle. Create mutex w. No security, false, and we don't want a name, so null. And of course at the end, as with everything, we need to close that handle. Then we'll pass the handle here to our thread. Okay, one moment please. So to to obtain a lock on the mutex, we can just we should be able to just wait on it. So here we just wait for single object and params mutex, comma infinite, and this will do two things in one go. It will wait, and once the wait is done, it will automatically set the mutex to the locked state. So in principle this could also fail. So for example, if you would from some other thread call close handle on the mutex, this would fail with an error. So we should check if this was successful. So if this is equals what was it, wait object 0, or rather if this is not wait object 0, then just break, or we could continue I guess, but if it fails it's likely to keep failing. And then at this point we know we have the exclusive lock, so now of course last thing to do is we need to unlock it. So release mutex, And this does more or less the same thing, but it should be much slower. So I removed here 0. You remember before when we ran this code, it took like a few seconds to complete. Let's see how long it will now take. And it's already much longer. Let's see how far we are. And you see we are not even close to finish. So using the operating system to do this mutex thing for us, that will take forever and ever and ever. So let's just kill it, and let's see if we could do it faster. So obviously the faster way is to use critical section, because this is a nice implementation of a fast mechanism that only when needed asks the operating system to do something for us. But let's say we don't have a operating system to ask. What could we do then? Also, this will give us a small insight into how the operating system internally implements such things. So we will define a volatile long Stern per spin lock. Then we'll define here a volatile long spin lock is equal to 0. That already counts as initialized, so we just need to. This is basically just a variable in memory, one integer, which we can set to 1 or to 0. But the problem, if we would like, so naively, one could try to do something like this. So if spin lock is equals 0, then, or rather differently, if spin lock is not 0, then spin lock, then sleep, or rather while. Now once this is done, set it to 1, but this will not work, this is the wrong way of doing it. And then once we are done, set it to asterisk. Asterisk, yeah. So we can try it, but this will again result in a right, we need to tell it how long to sleep. Let's say let's be fast. So we are already done, and as you see, my list does not have the right amount of elements, so it will also probably crash as you see it crashes. The reason is why this doesn't work, that between this check, so we actually could take a look the disassembly on it. Debug window, the assembly. Hello. Yeah. So so here what we do, we have a couple of operations. At some point we load and do this test. Test Rax is more or less this comparison here, and then it branches. So to more or less here. The problem is that these are like individual instruction, one instruction, another instruction, third instruction, and when these instructions are executed, what can happen is that this instruction got executed in one thread and in another thread as well. So now you have both threads that have seen that our spin lock is 0. Then both threads thinks, okay, now I can take charge. So then both will set it to 1 and do their thing. And this is obviously wrong, because only one thread at any point in time should do that. So we need to find a way somehow to make this checking and setting be done with one instruction, or at least in a way that does not allow the operating system scheduler to to interrupt the instruction sequence and jam some other thread's execution in there. And this is done using so-called atomic instructions. They are platform specific, although there is also a platform independent implementation in the STL. So if you want to you could implement an own spin lock using the standard template library. So this is, for example, the interlocked compare exchange function, which takes a address, a memory address, in this case our param spin lock. Then it takes a expected value. First it takes the value that it should set, let's say 1. Then it takes a expected value. So the way it works is it must find the comparent, the expected value in this memory region, and if it does so, it will change it to whatever we set it to change it to. And if it fails because it didn't find the right value, then it will fail and it will tell us what it got. So we need a variable. Let's call it long expected is 0. So we expect, of course, to be 0. And if this is not equals expected, then we need to sleep. What is it complaining? Unsigned. I forgot the unsigned. But this is not important. The unsigned, usually that can be ignored. Right. So it returns us what it found, and if it didn't find what it expected, then we sleep. And of course we don't need this. And then we just need to do 0. In principle this would even be fine, but there is also a function for this. Interlocked exchange. Since we kind of now have the exclusivity anyways, we could just use this equals 0, but let's do it the right way. And now when we run this, we will see that we'll get the right amount of entries in our list. And as you see, it was quite fast, so we didn't need to wait long, and we have the exact 10 million entries. Now, obviously, so these mechanisms, or these even mechanisms, when they don't get access, because in this scenario the access is very fast, so we can do such a spin lock, that works fine. But you could have a situation where you are synchronizing some threads to each other, and one of the threads will need a minute to execute its whatever it's doing. And at this point you would not want the other thread to, worst case is just without sleep, just a spin lock like this. So then it's spinning all the time. It's trying and failing and failing and failing. So such a spin lock will require more CPU time, and especially in situations where the lock might be held by the other thread for a long time, this would be extremely inefficient. So one thing to improve such a spin lock, of course, is to add such a sleep. But the best way is to actually use the right synchronization mechanism, like a critical section, because the way these are implemented, when they are waiting to get access, then the CPU is no longer executing any instructions. So the operating system will have written down somewhere in its internal data structures that this thread is now waiting for that object. And if the other thread, which is using the object, says, okay, I'm releasing the object, then the operating system will see in its tables internally which objects, because it may be more than one, are waiting for that object, and then one of them will be resumed. And the general idea of these critical sections, or this STD mutexes or QTQ mutex, is that if we go into this case of ours, so they usually all start out as a spin lock, and if they fail, then they start a significantly more convoluted internal process of allocating a STD mutex, then locking the STD mutex, and since at in all of these steps we want to ensure that we will not do something like in parallel twice in two threads. The whole implementation gets quite quickly quite complicated. Would you be interested in seeing such a implementation, or is this enough thread synchronization for one day? Okay, so since my voice is getting worse and worse, I think then we will stop here at this point. We only have about 15 or 20 minutes more to go anyways, so finishing a bit early is fine. What we should do is probably invent some homework. So let's do something that is simple. We already have, of course, the very simple first one here, but let's create also another one for that. Homework number 2. So but I did not demonstrate how to do that. Let's quickly add one demonstration. Okay, take count 64 gives us as a long the amount of milliseconds since the operating system was started. So if we do it twice, start, and then take the difference, where we subtract from stop start, then we'll get in milliseconds how long whatever we did took. Need to cast this to okay, so well, if we run it, then we'll see how long it took. It took about 2 seconds. So the task for the homework is section. Is that relevant? How to see how many operations to do? That should not be relevant. Yeah, then we will not do that. Yeah. Okay, so this is quite simple. You just have to modify the code a bit and put everything into one large function, and then you just run 3 instances of it. Ideally one after the other, so that they don't interfere with each other, and then it just writes down which of those mechanisms allowed the program to finish the quickest. Okay, so since that is that, I will upload the recording to the Moodle, and 2, 3 no, only 2. No, 3, we modified all of them, and up all the 3 projects again, so that we have that on the Moodle, and that's it. See you next week. Bye bye.